Hey guys, this is Howard, and today I'm here to present my number recognition program based on neural network. And I hope this presentation could give you an idea of how it works. And yeah. First, I guess you have seen a lot of artificial intelligence in your daily life. Voice recognition, face recognition, and auto-driven cars. Basically everything human can do is what AI is trying to replicate, though for now it's not as good as human mind. And speaking of AI, the most basic unit of it is a perceptron that simulates a neuron. And it has input, outputs, weight, and a threshold. Maybe for an example, we got a 3 for an input, and the other input is a 2. We have a weight of 1 and a weight of 2. And we have a threshold of 6. That meaning if we have the sum of our xj and weight j sum together, they're larger than 6, that means we got a 1, like a positive. And if it's not as large as 6, we got a negative, which is 0. We actually do like 3 times 1 plus 2 times 2, and that equals to 7. And then we do 7 minus 6, that's a 1. So that's larger than 0, the output is a true. Equally, if our threshold is a bit too large, like 16, then we will have minus 16 equals to negative 9. That will give us a 0, a false. Now we can proceed to sigmoid neurons, but that case, if we got a 999, that's like way larger than 1. But we still get the same true output as a 1 after we minus the threshold. So maybe that's not too representative of our input and output. Out inputs. So we have sigmoid neurons. Sigmoid neurons are basically a function still weight times our input plus b. Like the b is the negative threshold. Yeah. And it is defined z equals to 1 minus e to the negative z plus. Why it is like that? Because that's the most simple form that can give us a function like this. Like it's representative. Yeah, it's the next page. It can represent all the values from 0 to 1, and it's continuous on every single point. And it also logically makes sense, like very representative of our data from input to output. It reflects really good on the possibilities. And that's why we are using sigmoid neurons most of the time, like it's the most default thing. As for the architecture for neural network, we have the input layer, hidden layers, and output layers, just like our imitating the structure of our neuron network. And for input layers, as for neural network, we do the input layers and we can see the output layer, but the hidden layers in the middle, they are actually hidden. We absolutely have no chance to see them. And for single hidden layer, we just call it neural network. But if we have multiple hidden layers, it is called multi-layer perceptrons, MLPs, which we very often see on tech news if you check out New York Times or whatever. And you might think, what if we have a loop inside, we connect those hidden layers and it makes a loop? They'll be stuck in there, like timeout error thing. Actually, that is forbidden. We do not allow loop in neural networks. But if we define the time for each single neuron, like this neuron can only fire 3 times or for a limited time, that is possible. So the loop only exists for sometimes without creating an actual error. And to optimize our function, to optimize our fit curve, we have the cost function. The cost function describes how good our model is doing. It is basically a MSE, a mean squared error. Wait, 1 second. The define of C, W, B, that's the weight, that's the bias, equals to the sum of our y-axis, our prediction, minus the a, like the true value according to our dataset. Yeah, and that's what we are trying to minimize. We change the bias and we change the weight. The bias is basically our threshold and input. And gradient descent is also the similar idea. It is the process of getting to the minimal point. As we can see, for this local minimum, that's what we are trying to achieve. And by definition, we want to minimize our cost function, so it will always go down. So it's impossible for a function to stay in here because the parameters are not good enough. Like, it gives really large value for a cost function, but it can actually stay here. And when you make a small move at this point, it's gonna be larger than that point. So it will not stay larger values. That's it. I guess it's time to move on to the coding part. Hey guys, now we move on to the coding part and take a look at how the codes achieve this number recognition function. First, we import the TensorFlow, like the basic language library we are using in Python, and pyplot, which is the thing we use to plot graphs, and MNIST, MNIST. MNIST is the dataset by the US Statistical Department that give us those numbers for us to train. And then we just we input these numbers through X training, Y training, and X test and Y test. We put them into datasets. 50K of them are training datasets, and 10K of them are testing datasets that's already set in the MNIST dataset. We just load them in. Then we change every RGB value from 0 to 1, because that could save a lot of time, and that could be empirically proved. Like, the RGB comes from 0 to 255. We just all divide them by 255, and we can achieve like numbers from 0 to 1. And then we load a sequential function, which is a forward-feeding neural network, the most basic kind. First, we want to create an input layer that is flattened. A flattened layer kind of speed up our input process, but it's not necessary, of course. And then we create two dense layers, each consisting of 128 nodes. And these two are our hidden layers. And we want to use the activation function of ReLU, rectified linear function, which is like the basic and default for activation function. As for our output layer, we use a dense layer of 10 nodes, 0 to 9, with an activation function of softmax, which is like default for probability distribution. We want to compare like which probability is the largest for the number. Of course, then we compile the model with optimizer Atom, the default, and loss sparse categorical cross entropy. Well, loss function just evaluates how good your model is doing on the certain value, like high accuracy, high precision, etc. And we are talking about accuracy, like we want the most accurate prediction. So this loss function is calculated about accuracy. Then we train our model with an epoch of 3. Like, we go through every single dataset 3 times. And as we can see, the accuracy rises from 0.92, 0.96 to 0.97, like 97% accuracy throughout the 3 epochs, which is pretty good. This dot evaluate is the cost function of the system and gives us the main square root error. Then we save our model and load again to do the test dataset. And let's take a look at how our model deals with the test dataset. Well, of course, we cannot read this data, right? It's raw. So we input numpy, SMP, and we try to get, maybe we get number 2 out of the test set. It says it's a 1. Then we grab it and show the plot. Oh, exactly, it's a 1. That's pretty good. Let's grab another random number, like 23, out of the test data set. It's a 5. It is a 5. Good. Maybe we want to do another one. 45. Nice. It's also 5. Then I just thought maybe that's not fun enough. I mean, only playing with the test data set. So I draw a picture from Photoshop of my own. I draw 5. That is 28 by 28 pixels. Then I input it in using CV2 and OS, which are the very useful tools for input files. I change it into 28 times 28, which is like a double check, and I normalize it into between values of 0 and 1, and I put it in to our model. And let's see how it does. Exactly, correct. I think this is a pretty. So I think the model does a pretty good job in recognizing individual numbers. However, I still want to proceed on this model to make it able to recognize the series of numbers, like an IP or phone number, something like that. Thank you for listening.